Okay, so let's take a look at the solution for example 1.3, the Venturi meter, where we have two different columns at two different locations in the Venturi meter, and these columns represent the pressure at each location. You'll notice that the column for A is lower than the column for B, and that gives us some information on the pressure of A versus pressure of B. We'll talk about that more in the solutions here. So we were given the atmospheric pressure, 14.7 pound-force per inch squared. We were given the gravitational constant, 32.2 feet per second squared. We know the specific volume is 0.01604 feet cubed per pound mass. And we know that the change in height, the height difference between the two columns, is 10 inches, which basically, our H2 is, what we're calling, so this is 10-inch difference. We're looking to calculate the pressure difference between point A and B, and then which location is the pressure higher. So actually we can answer part B right off the bat here. So at location A, we have a column of liquid that is driven upward by the pressure at that location, right? There's atmospheric pressure acting downward. Location B, we have a column that is higher than location A, and that column is driven upward by the pressure at location B. Right? And again, we have atmospheric pressure acting at that location as well. Since the column at location B is higher than at location A, we have a higher pressure that's forcing that column higher than at location A. So the answer to part B is that the pressure is higher at location B. Okay, so let's look at the analysis here. So the pressure at location A, we're actually doing a calculation for absolute pressure, right? Because you'll notice here we have the atmospheric pressures in our equations. But the pressure at location A is just equal to density times gravity times H1, and then we have to add in that atmospheric pressure, right? So here we go. Atmospheric pressure plus density times gravity times H1. At location B, we have atmospheric pressure plus density times gravity times the addition of the two heights, right? Excuse me. So we're going H1 plus H2 is the total height of that column, and so that's the pressure at location B. If we want to figure out delta P, we just take PB minus PA, and you'll notice we have atmospheric pressure in both of these, both of those portions of the equation, right? So positive and negative, those will end up canceling out. We also have density times gravity times H1, and then density times gravity times H2, right? So what will end up happening is density times gravity times H1 will cancel off. The atmospheric pressure will cancel off as well, and we're just left with density times gravity times H2. And so here we have delta P is equal to density times gravity times H2. We mentioned in a previous lecture that density is equal to 1 over the specific volume. So you can see we've replaced density with 1 over specific volume. And the reason why is because the problem gives us information of specific volume, but we do not have we don't have any information on density, right? So we can figure that out just by taking the inverse of the specific volume, and that gives us our density. Gravity we're given, H2 is the height difference between the two columns, which we were given as well as 10 inches. And so we end up, if we plug in our values here, we end up with our equation. So this is 1 over specific volume, gravity, and then height. The height difference is 10 inches, right? And we're going to convert those inches to feet. So those inches will cancel, and we're left with feet squared over second squared. The feet square will actually cancel off with a portion of this, right? So we'll just be left with one unit of foot down here on the denominator. And then pound mass is on the denominator of the denominator. So that actually will move up to the numerator. And so what we find is that delta P is equal to 1,672.9 pound mass divided by foot times second squared. Now, our goal here is we want to figure out the pressure, or the change in pressure, in PSI, right? Pound force per inch squared. And so we need to do a little conversion here, in which case we're going to go from pound mass to pound force. And the way we do that, if we remember the equation F equals ma, so force is equal to mass times acceleration, well, we can say 1 pound of force is equal to 1 pound of mass times the gravitational acceleration of 32.2 feet per second squared. So the pound mass is going to cancel there. Oops, excuse me. The pound mass will cancel there, and we'll be left with pound force over foot squared. Oh, I'm sorry. So the feet squared are on the denominator, and the seconds squared are going to cancel as well. So we'll be left with pound force per foot squared, right? We're looking for PSI, which is pound force per inch squared, right? So instead of going from 50, so we're going to convert from 51.9 pound force per foot squared, we're going to say that 1 foot squared is equal to 12 inches squared, right? And remember, when you do this calculation, that 12 inches have to be squared. So what that means is we got to take 12 times 12, so this is actually 144 inches squared on this denominator. But the feet squared cancel, and we're left with pound force over inch squared. So we have a delta P, a change in pressure of 0.36 pound force per inch squared, and that's our final answer.